Welcome back to ECE 320A. Homework 1 is due in a week, and you can submit that or turn that in on that day in class if you would like, but I think I'm giving you a little bit more time if you want to turn it in a little bit later than that through the Dropbox on D2L. Or if you would prefer, you can actually turn it in to my mailbox physically in the ECE building if that's more appropriate for you, and that just depends on how you want to do it. You should be reading or have already finished reading Chapter 10. Today what I want to do is work through an example of complex power, and when I say complex power, you should be thinking about the triangle, where the horizontal axis is the real power or the average power, the vertical direction is your reactive power, and connecting those two head to tail, and then finding from, let's say, the tail end of the power arrow to the tip of the reactive power arrow, that's your complex power, which has a magnitude, the magnitude being your apparent power, and the angle, and that angle tells you something about the power factor of that particular piece that you're looking at in terms of the complex power. And you can look at the complex power for all of the different parts of your entire electrical circuit or system. We'll look at something that's maybe closer to one of the homework problems on the second goal, which is to look at a two-terminal element and find or compute its complex power. And I want you to make sure that you're clear on the passive sign convention and what that means relative to is power being absorbed or supplied. And you could have the real power being absorbed and the reactive power being supplied, or vice versa. Or they could both be being absorbed. They don't have to both be one or the other. They can play with whether they're absorbing or supplying that power. Then we will look at developing some complex power formulas based on really just complex algebra, and we can create formulas that involve only currents or only voltages and the impedances. Obviously, they have to have something. The complex power is volts times I star, or the conjugate of I, and you can replace V or I with its impedance relationship via the generalized Ohm's law. Then we'll get into multiple loads, which really, if you look at it, this example is a multi-load example. We've been playing with this a lot, or I've been giving you this, and this is what you probably were doing this weekend. Is that true? As I left the office, somebody said, you might have a lot of classy eyes looking at you. What? Not in my class. They're going to be bright-eyed and bushy-tailed, right? Because you're anxious to learn about complex power. Can't wait. That's what I said in your defense. But here we have one load could be the transmission line, and another load could be what we're calling the load. So this really is two loads. It's just typically we think of the load as being the load, and the transmission line is maybe what's lost in transmission of that power from the source to the load. Let's look at finding the complex power associated with each of these pieces and parts. And I already put this down thinking that probably if you couldn't quickly sketch it while I'm talking, you could at least go back and leave yourself enough space because you have this somewhere else in your notes. Or you can wait and get it from the PDF that will be on the D2L website as the notes. Here's what I want to make sure that we're very clear on after today's class, and that's this passive sign convention. If we want to find the complex power of the source, we need to establish, is this power, this complex power, being absorbed or supplied relative to the way that we've defined our current and voltage labeling. That's really all that we're doing, is define some labels, and they don't necessarily have to be accurate. They can just be labels, and then we assume those are correct, and then we define what we mean by the passive sign convention in that notation. In this particular illustration, I'm showing that the current, as I've drawn it, that's, let's say, the positive current. That's the current that I would like to be positive. It may end up being negative, but the signs will work out as long as we follow the following convention. I'm saying that the current is going into the positive terminal, meaning it goes into the positive terminal before it goes in through the rest of the element or network and then exits out the negative terminal. That's what I mean by going into the positive terminal, the current going into the positive terminal. So it's defined as the current direction that I've sketched into the positive terminal, and I won't usually say all of this in parentheses, but then it passes through the device and then exits the minus terminal. If we have that notation for our current and voltage and the polarities, then we are going to agree, because of the passiveness of our systems typically, which is then the passive sign convention, we're going to say that that represents absorbed power by definition. And the absorbed power is V as a phasor times I as a phasor conjugated. Now, what I haven't done explicitly is indicated that those have to be in RMS units to have this formula. So maybe I should, as we're first learning this, we need to make sure that we are using RMS units, or if we're using maximum values for those magnitudes, what do we have to do with this formula? We'd have to divide by 2. It's now 1/2 V max I max conjugate. Let's now find the complex power of the source. Now, if we're doing that, what's the expression that we are going to use? What's our expression for the complex power of this source? How do we want to define it, or how do we define it? If I said, give me the expression for the absorbed, or how much complex power that source is absorbing, what would the expression be? And how do you figure that out? I'm going to call that this complex number S sub S. The way that I have labeled my diagram, I have a voltage. I'll do the easy part. I know it's V, and then what is it? I have to use the passive sign convention, and the passive sign convention said if I'm trying to compute the absorbed power, what do I need to be true? The current needs to go into the positive terminal. Is the current that I've defined, I sub S bar, going into the positive terminal of this particular piece of the power or of the system that I'm trying to compute? Is it going into the positive terminal? So now I want to know, so there's two different ways of looking at this. You could say my source is supplying power or it's absorbing power. And those should be just the opposite in signs, correct? Typically you would think, okay, the source has to supply power if it's the source. But if it's supplying power, then the current needs to be coming out of the positive terminal and not going into the positive terminal. Is that making sense? But if I now said I want to compute this expression for the absorbed power, then is that current I sub S bar going into the positive terminal of V sub S bar? And the reason why I keep asking is because you keep saying yes, and it's actually no. Why is that? So I made a big deal about going into. If the current, as I've drawn it, goes into the positive before it goes through the element and then out the negative, then it's going into the positive terminal. In this case, what's really happening? I sub s is going into the minus, through the element, and then out the positive. It's not into the positive. Do you see the difference? So, if I'm interested in the absorbed complex power, then if the current was going into the positive terminal, it would look like that. But since it's not, that's the way I would have to define the power absorbed, the complex power absorbed by this in this circuit, the way I've labeled it, with V sub s and I sub s bar. But just the opposite of being absorbed is supplied. And if those are opposite in polarity, supplied and absorbed, then with the way that I've defined the notation in this circuit, if I know V sub s bar, and if I can find I sub s bar, then I can compute the supplied power of that complex source using this formula. Is that making sense? And the reason is because of the way that I have sketched this, I is actually coming out of the positive terminal, not going into the positive terminal. All right, so let's look at the power supplied by the source. And to find that, I can find my total impedance, and those just add vectorially but by the real parts and the imaginary parts, keeping track of those two pieces. I now have the line impedance, which is 2 plus J1, plus the load impedance, which is 78 plus J59. Here's the line, and here's the load. Or this, I might say, is Z sub L, little lowercase l, and this is Z sub capital L. This now allows me to compute the total impedance as 80 plus J60. And if I now want to compute, the current, then that's going to be the supplied voltage divided by the total impedance. And if I'm taking the ratio of these, I know that I was given my supply voltage to have a magnitude of 220 at a phase of 0. And I've just found my impedance total. It's in rectangular form, but a lot of times if I'm taking the ratio, dividing or multiplying, it might be easier to keep track of these in polar form, which allows me then to think about this impedance as also a triangle, meaning now I have this angle theta sub z, and this length is the magnitude of the impedance. And I hope that you can see that that's a 3, 4, 5 triangle, or similar to one. So we have 60, 80, or z sub t is 100. So we now have the magnitude of z sub t is the square root of the real parts plus the square root of 80 squared plus 60 squared, real part squared plus imaginary part squared, square rooted, and theta sub z is this angle that has a tangent of 60 over 80. and that is roughly 37 degrees. Is this making sense? I can now compute my I sub t, just dividing 220 by 100. I can maybe even do that, just move my decimal place a couple of places. I now have 2.2, and I can actually subtract 36 from 0, or 37 from 0, to get an angle of my current flowing through that network as a minus 36.87 degrees. And since my voltage was in RMS, my current is in RMS magnitude values or numbers. Questions on this? Now I know what current is flowing out of that source. And I can immediately use my complex power formula. I can now say, okay, here is my complex power supplied by the source is V sub S, I sub S conjugate, or 220 at 0, 2.2 at, if I go ahead and change the sign, which is what happens when I conjugate a complex number, I now have my complex power supplied by the source is 484 at 36.87 degrees volt amperes. And if I do my cosine plus J sine on 37 degrees, I end up with the real part of that power being 387.2. The reactive part is 484 times the sine of 36. That's also positive, and that gives me 290.4. And really then, this is now our power supplied in both the real part, which is in watts, and the reactive part, which is in vars. And now I know the pieces that make up the complex power supplied by that source. And if you wanted to, you could draw the complex power triangle of that source. You would say, okay, I have P going roughly 390. Then I'm going up positive 290. So here's P. And here's Q. And now if I wanted to, I know that this is that 484 at an angle of 36.87 degrees. And that's the picture of the power triangle associated with this system or this circuit and what the source is doing for us. Questions on that? Yes. What am I doing? Yeah, that's what I have there. Why? What was the question? Is that the question? Where did the P come from? So the P is the real part. It's 387.2. And the reactive part is 290.4. So I take the P's horizontally. The Q's are going to be vertically. In this case, is Q positive or negative? What do you know about the load? It's inductive. And that makes sense since it was an inductor. Did that answer your question? Oh, tell me my handwriting is poor. I thought you were asking about the... Yes, that's supposed to be... Is that better? If I draw a horizontal line through it, maybe. That's 387, not 3. So it magically didn't change numerical value between the P up above and the sketch of the complex power. If it does on the exam, you'll only lose 99 points out of 100. I'll give you 1 point for partial credit if you make that kind of a mistake. I won't be quite that harsh. Other questions? What about the complex power of the load? We need to ask our same question, and now we say, okay, if I want to say the complex power absorbed by the load, what's the expression for the complex power of the load? And my question hinges on, is that current that I've labeled going into the positive terminal of my load? Yes, because it goes into the positive terminal before it continues through the load elements themselves and out the negative. This then is set up to give me the absorbed power at the load. This is now going to be S sub load is going to be plus, by the passive sign convention, V sub L bar, that's the voltage across the load, I sub L bar star, but this is really just I sub whatever I defined it. I'm really going to... And this is the power absorbed by the passive sign convention. But we can now, so if we now have the complex power of the load is this V sub L bar, I sub T bar star, I know that V sub L is Z sub L, the impedance of the load, times the current going through that load, which is I sub T bar. But then I need to multiply that by I sub T bar conjugate. And what is a complex number times its conjugate? Do you remember? That's the magnitude of that complex number squared. I don't have to worry about the angle anymore. So I times I star is just the magnitude of I squared. Or now I have Z sub L is I sub T's magnitude squared. Z sub L was this 78 plus J 59. I sub T had a magnitude of 2.2, and I can square that. And if I multiply by 2.2 squared and push that through the two parts of my complex impedance, I end up with the complex power absorbed by the load is now this 377.52 plus J 285.56 volt amperes. Or if I wanted to, I could find that in polar form. And that's now the complex power absorbed by the load, which means I have 377. Those are sevens. Yes. Yes. So now the question was, where did that expression come from? If we had A plus JB, let's say that's I sub T bar, then we would multiply that by I sub T conjugate, which is A minus JB. Now if we do all of the, we FOIL with this, first, outer, inner, last. I didn't know that when I was growing up. We didn't use that, but that's apparently what you used, FOIL, to compute these. We have A times A squared, JBA. Then we have minus JBA or AB. They commute, so I'm not going to worry about it. And then I have minus J squared B squared. These two cancel. J squared is square root of minus 1 squared, which is minus 1, and now I end up with A squared plus B squared, which is the magnitude of I sub T bar squared. That's where that came from. That's why I could quickly now only worry about the magnitude of that current of 2.2. I could throw away the angle. I'm not really throwing it away. It's absorbed in all of this calculation. Did that answer your question? Other questions? Yes. So now the angle here of the load, the question was, I can see a difference in my angles. There's an angle of the load of 37.1. There was an angle of my source somewhere of 36.87. And now what we will see is that we need to keep track of these angles because powers add vectorially, meaning we need to keep track of the real parts. So we can add the real parts, we can add the imaginary parts, and then worry about the totals that way. So we have to keep track of these, and so this angle should be probably generically different than the load's angle unless what? It depends on the line, what's happening in the line. If the line was purely real, then we wouldn't have any angle or phase shift occurring in the transmission line. But we do have some phase shift because we have an inductive line or an inductive transmission line. So there should be some differences in the angles between the source side and the load side because of that complex impedance in the transmission line. That's why we have this difference in angles. There is our power of the load. Maybe your boss is concerned about how much he's paying for this power. And if he's concerned about the power expense, then he's probably worried about the power factor. And to get a small power factor, you need that angle to be closer to 0. It's not that close to 0, is it? 37 degrees. What is our power factor of the load? If I now say the power factor of the load which is PF sub load, that's really just this ratio of the real power divided by the apparent power of the load. But the apparent power divided into the real part, if you remember our formula for P load, that's just the magnitude of this times the magnitude of the current times the cosine of the angle of the load impedance, which now says that we could compute the power factor by just taking the cosine of theta sub L and noting what the direction of that reactive power was, whether it was positive or negative. In this case, that was 37.1 degrees, so I need to make sure I'm clear on my 7s and 1s, don't I? So it's 37.1 degrees, and if I compute that cosine, I end up with 0.798, and is the current leading or lagging in this load? Lagging is if you have an inductive load. This is now 0.798 lagging. And maybe the power company charges you extra if your power factor is 0.8 or less. It probably goes up even more if you get to 0.75, 0.7, etc. Your surcharge or this additional charge. But that's now lagging because it was an inductive load. And you need to tell me both of those pieces. If I ask for the power factor, you can't just give me the numerical value. You need to tell me, is it lagging or leading? And you can do that by looking at Q. You can look at the angle in terms of the sine of the angle. In this case, the sine of the angle was positive, which would it would disappear when you take the cosine, so you have to kind of remember the sine of your angle. Questions on the power so far? And if you wanted to, you could sketch your power triangle for this piece of the circuit. It would have a real part of 377 and an imaginary part or a reactive part of 286, and you have the hypotenuse, which is 473, which is your apparent power. All right, since we're continuing what if we wanted the complex power of the line? Energy is conserved, isn't it? So over time average, the powers are going to be conserved. Meaning we already have one piece, the source. We have a second piece, the load. The only piece left is our line. The line and the load should sum up to give me the total, which was what was being supplied by the source. Meaning we could find the line's complex power by taking the complex power supplied by the source and subtracting from that the complex power of the load without needing to calculate V and I at the line. But we could do it either way, and we should come up with the same answer. In this case, it was this 387.2 plus J 290.4 minus 377.52 plus J 285.56. And if we take the difference of those complex numbers, hopefully I did the math right, and we get about 10 watts lost in the transmission line in this example, plus J 4.84. questions. I could ask you a lot of different questions. I could go back and say, what's the apparent power that the power company is seeing or having to deal with? Can you find that in the notes? And what is the apparent power? It's staring us right in the face. We have all sorts of powers going on, don't we? And it's complex. Play on complex, but sorry, that's not on the tape or the recording, is it? Need to keep you awake, maybe. We have real power or average power. Where is that on this diagram? That's P, that's the horizontal. We have reactive power. That's Q, that's the vertical. And we have the complex power, which is this line at an angle, because the complex power is a complex number. It's a length at an angle. But if I wanted to find the apparent power, what is that? That's just the length of that hypotenuse. So that's 484. That's our apparent power. The apparent power of the source is then V sub S, I sub T, their magnitude, which is 220 and 2.2, which is 484 volt amperes. And that was in the triangle. Everything should be consistent. We could say, okay, what's the power factor at the source? Is that the same as the power factor at the load? Generically, no, is it? What is this? Well, this is now cosine of, let's say, theta sub S, which is really theta sub V minus theta sub I, the angle of the voltage at the source minus the angle of the sine of the current at the source. Our voltage angle was 0. The current was a minus 36.87. Their difference now and this sign is not really showing up there explicitly, but that was a positive sign, which now tells us this is 0.8 what? Have a 50-50 chance. Flip a coin, right? If you're on the exam, probably you can do better than that. You can go back and look at your triangle, and what are you keying on? Is that vertical direction up or down? If it's up, it's inductive or it's lagging. What about the, yeah, we've already computed the power factor of the load, haven't we? So this one's slightly different than the power factor of the load. Questions on this example? Yes. Well, the power factor itself, I think the question was, can you tell whether it's leading or lagging by just the magnitude of the power factor number? And the answer is no. You can't tell. Somebody could give you 0.8 and they need to tell you, is that leading or lagging? Because if they just give you the number, you don't know whether that's inductive or capacitive. They have to tell you that additional piece of information. So you need to know, is my reactive power positive or negative? Do I have an inductive load or a capacitive load? Or what's the angle of my impedance of the load, or whatever you're asking? If your angle is positive, then it's lagging. So if they give you the expression cosine of theta sub s and they show you what that angle is, yes, then you can figure out if it's lagging or leading. Once you operate on that with the cosine, the angle goes away, or the sign goes away, doesn't it? S-I-G-N. So you have to know what is that angle, and it's lagging. Let's look at an example that's very close to one of your homework problems. I think it's the first homework problem, which maybe you've already completed, I hope. But let's say that we have a two-terminal element. And suppose that this is my voltage V, and this is now my current. And actually, I'm going to work this with time domain expression. So let me just call that little v of t. And I'm now going to ask, find the complex power for this element. And that might be some combination of resistive, inductive, capacitive elements. And they might be interconnected in some weird way. All you know is V and I. Suppose you're told that V of t is now 100 cosine omega t plus 15 degrees volts, and I of t is now 4 sine of omega t minus 15 degrees amps. And you're trying to compute the complex power for that two-terminal element. And omega, if we're in the United States, and this is a power example, what is omega? 2 pi 60, isn't it? 377, roughly. In our case, it really doesn't matter. We just need to look at magnitudes and angles to find these powers. But before we do anything, we need to make sure that we're looking at or dealing with the same trigonometric waveform. We can't be computing these expressions with a sine and a cosine. We have to make everything consistent. And typically we make everything, turn everything into a cosine. Let's convert this current into a cosine, which doesn't change the magnitude, it doesn't change the frequency, but what does it do? Do you remember? Cosine of x, or sine of x, is cosine of x minus 90. You can verify that by one of your appendix formulas if you want. Yes. Pardon? No, you don't want to add 90. The question was, do you want to add 90? You can, but it's not going to give you the consistent answer. So the cosine axis is here, and the sine axis is behind it, 90 degrees. And you don't want to confuse those sines and cosines. So you do want to make sure that you're keeping sine of x is cosine of x minus 90, which this is now going to be this minus 105 degrees. What's the real power based on this information that we now have? So what is my power formula? You remember? VI. So if that would be the instantaneous magnitude, wouldn't it? But we want, this is a capital P if you can't read my note handwriting. I want the average power. So I'm assuming this is happening for a long time and I want capital P. In terms of these values, what is that? That's the maximum, isn't it? And what's this? This is the maximum of my current. If I use those numbers, then I need this to be 1/2 Vmax Imax, just the numbers, cosine of theta sub V minus theta sub I. That's my average power formula or expression. Now, do I have the sign correct? I've assumed a plus sign. Is that correct? Judging from the passive sign convention, should my sign for that real power be positive? Is the current that's given to us going into the positive sign? Yes. Is everybody clear on that? That positive sign needs to be there. And now I have 1/2. Vmax was 100. Imax was 4. Don't you wish that was Imax? Then we could just sit back and watch, huh? Sorry. Did anybody? We could draw. No wonder I wanted to do an Imax. What is this? Red box, right? Isn't that what we had at Red Box the last time? No wonder I was thinking movies. All right. What's theta sub V? That was 15. And we need to make sure that those were using cosines and cosines in theta sub V and theta sub I. This is now minus 105, or we now have 200 cosine of 120 degrees. Whoa, that flips us beyond 90, doesn't it? Now we have a negative number coming in. This is now an average power of minus 100 watts absorbed. Using the passive sign convention, which really means what? That particular element is supplying power to the rest of the circuit, since it's a negative absorbed power. That's what that means. So I have minus 100 absorbed or 100 watts supplied to the rest of the circuit. What's my Q? What's the reactive power? I don't know if we had that in a box or not before. So this is 1/2 Vmax Imax sine of the angular separation. This is now 200 sine of 120 degrees. This is now 173.2 vars absorbed by our passive sign convention. And then if you wanted to talk about this, you could say that two-terminal element is actually delivering 100 watts to the rest of the system . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . through the two terminals that were given, and it's absorbing since they were positive, it's absorbing magnetizing VARs at its terminals. The complex power then of that element, S sub E, is minus 100 plus J 173.2 volt amperes absorbed. And now you should be able to work at least your first problem on your homework if you haven't already, based on that example. Yes? So this is, the question was, since the reactive power is positive, then whatever was in that box between those two terminals is effectively looking inductive. It could have been a bunch of inductors and capacitors, but its net appearance at those two terminals is inductive. It could have been a lot of different things in there, we don't know, but in terms of that black box description that we were, well, it's a green box, but that description, we don't know what all's in there until we compute, and now we say, well, it's looking inductive. So the net effect of whatever is in there, however it's interconnected, is inductive looking at those two terminals. I'm not sure if that's answering your question or not. But you could have a lot of different things in that box, and what this is telling you is that effectively looks like an inductor. You could replace that if you were told the frequency, then you could compute the inductor that would represent that amount of VARs, magnetizing VARs, being absorbed. You could say, here's my equivalent element. And you would also have to put what? A negative resistor in there since it's supplying power, if you wanted to do something like that. Other questions? Let's look at, we've already done one, but we can actually create, just playing with the complex numbers, we can generate several different expressions that are equivalent. If somebody says, okay, here's my complex power, that I know in RMS units is the voltage times the complex conjugate of the current. But maybe somebody only has the current, but they know the impedance, and they don't want to mess around with this indirect step of computing the voltage. Then that's what we did in our example. We simply replace that voltage with Z times the current going through that impedance. And we derived that result, that I times its conjugate is the magnitude of I squared. So that now we can say that this is the complex power of a piece of electrical circuitry is the impedance times the current, magnitude of the current squared. Let me be consistent, I guess. I was calling that I sub RMS. That's a complex number, but we can take the magnitude of that and square it. But we also know that Z is some R plus JX. And now if you distribute that squared current through those two terms, you have R times I RMS squared plus JX I RMS squared. And that simply represents the real and reactive pieces of a load or a circuit element. Meaning this is now P plus J, and this is now Q. And that allows us to say that the real power P, if we know the equivalent impedance, it has a real part, then we can use that to find the real power if we know the current through that device, and we know the reactive power if we know the reactance, X. And those formulas all now hinge on knowing the current. And you could then say that these are current formulas. If you know your current, then if you also know the equivalent impedance, then you can use these formulas to compute the real and reactive power in that particular piece of your circuit. We can do the same kind of analysis by saying, what if we just have the voltages? Let's look at the voltage formulas. We start with the same expression. We have this VRMS, IRMS conjugate. And now we want to keep V, which means let's replace I, or rewrite I in terms of V and the impedance. And that's now V RMS over Z conjugated. The whole thing conjugated. V could be complex, Z is complex generically. What's the complex conjugate of a quotient? A over B star is A star over B star. It's just the quotient of the conjugates. This now allows us to write down an expression for the complex power knowing the voltages and the impedance. But this now simplifies because of what we know about complex numbers times their conjugate. This is now the magnitude of the voltage dropped across that impedance squared divided by the complex conjugate of the impedance. And that will generate a real part and an imaginary part, and that will give you the real power and the reactive power of some circuit. And it may depend on what you are playing with. You might want to manipulate the formulas to give you an expression that's more convenient for your analysis that you're using, that you're doing. That was the reason behind examining these particular formulas. Questions? Let's look at, now that we're playing with power, suppose that we have a more complicated network. Let's look at the total complex power in a network. Here's something that I think is kind to us in terms of what we need to keep track of or not keep track of. How these, let's say, subsystems in this network are interconnected, or the interconnection structure. By that I'm saying whether load 1 is in series with load 2, which is in parallel with load 3, which that combination is in series with load 5. This parallel series combination, or the way that it's interconnected, really doesn't matter when we're dealing with powers. We can just compute the subsystem's complex power and then vectorially keep track of or add up those powers. That's the idea. Doesn't matter if some were in series, some were in parallel. We just look at the pieces and play with the pieces. Let's now let what I will call subsystem L, so that's supposed to be a lowercase l, have the following complex power. Let's say that that complex power is S sub L, which is P sub L plus J Q sub L. And now maybe we have capital N such subsystems. If we do, then the total average power, or the total real power, can be found by simply summing up all these individual real powers. Units haven't changed, that's still in watts. Likewise for the reactive power. The total reactive power is this sum from 1 to capital N on the subsystem's reactive piece. And those could be different signs. You might have some positive Q's, you might have some negative Q's. You just keep track of the signs algebraically. That has units of VARs. And the total complex power of this entire network of capital N subsystems is now just P sub T plus J Q sub T. Or, keeping track of our formulas again, one thing that you want to keep track of, or keep clear in your mind, is that we can't find the magnitude or the apparent power of that network. That's not the same as summing up the individual apparent powers. You have to only sum up the reals and only sum up the reactive pieces in order to come up with the total complex power. This is not the same. Meaning, if you wanted to think about what was happening and you simply had two subsystems, this may get a little bit, well, view this as art. I ran into somebody and never mind. That was in the ECE building, and he started talking about poetry. And I said, well, it's all art in this building anyway. So view this as an art. Suppose we had Q1, I'm sorry, P1, and now Q1. And that would give rise to this S1. But now if you had another subsystem that was maybe P2, and maybe it had a capacitive reactive piece, so here's P2, and here is Q2. Now we have S2. What's the total complex power? So I need to add up my vectors, don't I? I can't just add their lengths. If I added their lengths, I would get a much longer vector. That's what that earlier formula said. If I wanted the total power, then I'm starting here and I'm going to that location, and that's S sub t. And that length, if you looked at that triangle formed by S1, S2, and S sub t, you know that S sub t is shorter than the lengths of S1 and S2. That's all that earlier formula was telling you. That's something to keep track of, and that's kind of a pretty picture. I find it kind of, that's not pretty.